This comes out of section 11.1, permutations. First piece of this example, we're asked to evaluate 6p4 without a calculator. Now, no one on your diploma exam is going to ask you this question because no way is taking your calculator away from you. But if we know what the p means, 6 factorial divided by 6 minus 4 factorial means we're doing 6 factorial divided by 2 factorial. Well, 6 factorial is 6, 5, 4, 3, 2, 1, and 2 factorial is only 2 times 1. So what do we have left over here? We have 6 times 5 times 4 times 3. Now, some of you are better at mental math than others, but basically 6 times 5 is 30, 4 times 3 is 12, 12 times 30 is 360. So not as impossible as it might have first sounded. Mainly what I really want you to get out of an example like that is to know what p means, what permutation is actually doing, and be able to cancel things out. And I'll show you in a next example why that might be more useful. It's kind of a strange example in that it's worded as a show that 120 factorial plus 119 factorial equals 121 times 119 factorial. You're not going to get proofs in this section as a test question anyway, but as a teaching example, it's somewhat useful. And just to show you that, I know that my calculator won't handle these. These numbers are too big. If you try punching in 120 factorial on a regular calculator, it'll say digit overflow and you're done. You can't show just with huge numbers that these are equal. What I can do though is say 120 factorial is 120 times 119 times 118 times 117, etc. So in other words, it's 120 times 119 factorial plus 119 factorial, or in other words, 1 times 119 factorial. Now, there's a common factor there, which is 119 factorial times 120 plus 1, which in other words is equal to what the other side said, which was 121 times 119 factorial. So not really, again, a real exam style of question, but something worth showing you how factorial can work and how you can work around numbers that you can't handle. Next one is more of a test or quiz type of example. You would be asked something like this, or some form of this on a test. Say, solve this algebraically. If you see that, you basically need to go right back to what does p mean. It means that it's n factorial over n minus 2 factorial equals 72. I can't just cross out factorials here as much as some of my former students would like me to, but n factorial I remember is n times n minus 1 times n minus 2 times n minus 3 times all the way down to 3 times 2 times 1. On the bottom I have n minus 2 factorial, which is n minus 2 times n minus 3 times n minus 4 times all the way down to 3 times 2 times 1, and all that equals 72. Well, everything from n minus 2 down is common on the top and the bottom. So really what I have is n times n minus 1 equals 72. So in this case, this turns into a quadratic question where I've got n squared minus n equals 72, n squared minus n minus 72 equals 0. This thing factors nicely to be n minus 9 times n plus 8 equals 0. So n equals 9, or n equals negative 8. When you're doing NP2, n would have to be a natural number. This negative 8 answer here is extraneous. You can't give negative 8 as an answer. I think of it this way: you can't have negative 8 objects and be asked to arrange 2 of them. But you can definitely have 9 objects, be asked to arrange 2 of them, and you can do 9p2 on your calculator, and it will tell you that that answer is 72. So these algebraic solutions often end up being a quadratic that you solve at the end, but given that we did cubics and factoring and everything, somebody could try to get creative and give you a question that combines a permutation notation like this with then factoring a cubic or a quartic fourth power function and coming up with the answer to it.